Hello and welcome back. It turns out that if you look at the fundamental theorem of calculus part 2 from a different point of view, you get what's called the net change theorem. The net change theorem essentially says that the net change in a function, big F of x, over an interval from a to b, well, one way you could write that is big F of b minus big F of a. That would tell you the change in that function from a to b. But that can be computed as the integral from a to b of big F prime of x dx. Now this should look very familiar because this is the fundamental theorem of calculus part 2, just written in a slightly different way. There are two changes that are made. One is that the left and the right hand sides of the equation are flipped around. And the other is that instead of writing little f of x, we're writing big F prime of x. Now we did this actually in the first page. Let me just zoom up to the first page where in the first video, we wrote a little statement off to the side. Right after we came up with the fundamental theorem part 2, we rewrote it where instead of writing little f, we wrote big F prime. Because we noticed that big F here was representing the antiderivative of little f. So the derivative of big F was little f. So we just replaced little f with big F prime and wrote it this way. And we were noting at that point that the integral is essentially undoing the derivative. So the big F, if you take the derivative, then you take the integral, you get back to big F. So here, we're looking at the net change theorem, which says exactly what we wrote down right here, but just has the left and the right hand sides of the equation switched around. So just looking at it from a slightly different point of view. We go back to the net change theorem. So if you want to find the net change in position, for example, which would be displacement, from t equals 2 to t equals 3, well, one way you could calculate that is by taking the difference in the starting position and the ending position. So final position minus initial position, s of 3 minus s of 2. But the net change theorem says that you could also calculate the net change in position using the integral from t equals 2 to t equals 3 of s prime of t. Now s prime is just the velocity function. So here, this is like s prime of t, right? If the function under question, the big F here, is the position function s, well then the derivative of that is the velocity function. Now just as an aside, if instead you wanted to calculate the total distance traveled from t equals 2 to t equals 3, then what you would do is calculate the integral of the absolute value of the velocity function. The absolute value of the velocity function would calculate speed here, where speed is always going to be a positive number. So this would count all movement as positive. Now some other examples would be the net change in volume, big V of T, of water in a tank. Well, one way you could calculate it is the ending volume minus the initial volume, so the final volume minus initial volume. But you can also calculate it by taking the integral from the t1 to t2, so the start time to the end time, of the derivative of the velocity of the volume function. Now here you might wonder, like, well, why would you need to do that if you had the volume function to begin with? Well, maybe you, let's say, don't have the exact volume in the tank. Maybe all you have is a tank and you don't know how much water is in the tank, but you can figure out how much water is flowing into the tank. Let's say your hose it has some kind of meter that says, okay, this is how much water is flowing out of this hose and into the tank. Well, then what you could do is set up the integral right here. If you had this V prime, this change in the volume, how much water you're adding into the tank, well, you could integrate that from the start time to the end time, and that would give you the change in the volume. So it's a little bit contrived of a situation, but we're just trying to tie together some ideas here, looking at the fundamental theorem of calculus both forward and backwards. Another example would be the net change in population. Let's say we say little n of t is the population. Well, the net change could be represented as little n of t2 minus little n of t1. So this is the final population minus the initial population. Or by the net change theorem, we can integrate instead from t1 to t2 the derivative of the population function. So this is the rate at which population is changing over time. These are two different ways of calculating the same thing. There's a big blank space in that page of the notes. And then we get to example 4, where it says, suppose the velocity function of a particle is v of t equals t squared minus t minus 6, and this is in meters per second. It says find the displacement, where displacement means change in position. Change in position. In fact, if we want to use our word, we can write this is the net change in position of the particle during the time period from t equals 1 to t equals 4. All right, well, the displacement we just said is the net change in position, which we could write as the ending position minus the starting position. It's s of 4 minus s of 1. But by the net change theorem, we can say that this is the integral from 1 to 4 of the velocity function. So I'm going to write the velocity function out. This is t squared minus t minus 6. We'll put our dt. Don't forget our integral sandwich. And this is the velocity function. So the reason we're doing this, we can do this, is the net change theorem. And we can evaluate that integral by the fundamental theorem of calculus part 2, or the evaluation theorem. We just need an antiderivative. So t squared will add 1 to the exponent, divide by that exponent. T, add 1 to the exponent to give you 2, divide by that exponent. 6 picks up a t. Then you plug in the 4. Put a minus. We're going to open up parentheses because we have more than one term. And we have 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. And eventually you're going to get negative 9 halves here, which is negative 4.5. And then the units here are, let's see, units of distance was meters. So negative 4.5 meters. So we went 4.5 meters backwards. All right. Actually, if we look at the picture over on the right side, it makes sense. Here's the velocity function. The integral of the velocity function from t equals 1 to t equals 4 is going to be negative because there's more area under the t-axis than there is above the t-axis. So more area out to the velocity function from the t-axis that's underneath the t-axis than there is out to the velocity function above the t-axis. All right, so some of these areas cancel each other off. So this positive cancels a little bit of this negative, and then the leftover negative is negative 4.5 meters. Now it says find the distance traveled by the particle during the same interval from t equals 1 to t equals 4. Notice this is asking something slightly different. Originally, we were asked to find displacement, which is the net change in position. So we could use this net change theorem. But now we're asked to find the distance traveled by the particle. So the distance traveled, what we'll want is to count all movement as positive movement. So that means we're going to take not just the integral of the velocity function, but the integral of the absolute value of the velocity function to capture all movement as positive movement. Now, one of the things we're going to need in just a moment is to figure out where is the velocity 0, or, well, specifically where is it positive and where is it negative. So we need to figure out where the velocity function is 0 first. Do a little sign analysis. You might think back to when you had to find the total distance traveled given a position function, and you had to find those t values where the particle was changing direction, and then do s final minus s initial in absolute values for each of those intervals. For all the movement that was positive and then all the movement that was negative, you had to do a change in position and put absolute value bars over it. Well, here we're going to do that same kind of thing, except when we break up our intervals, we're going to be breaking up into separate integrals. So we'll have a separate integral for each interval. Let's get there, because I know that sounded pretty confusing. We'll highlight when we get there. I can't tell you how many times I've said interval when I meant integral, and integral when I've meant interval. They sound so close to each other. And yet they're so different. Okay. So here we've got the velocity function is 0 when t equals -2 and t equals 3. We had to factor a little bit here. So we're going to make a little sign analysis chart for our velocity function, which was 0 at those two places. And we can plug in a little t value that's less than -2, and we're going to get a positive velocity. Then it'll flip signs and flip signs because of those odd multiplicities, those odd exponents for those factors. And now we're ready to go. Bye, I'm ready to go. No. Now we're ready to figure out the total distance traveled, which will be the integral from -2 to 3, oops, -2 to 3, from 1 to 4. Just saw numbers and wrote them down. The interval here is from 1 to 4. That's where we're trying to find the distance that we're traveling over. Of the absolute value of the velocity function. That'll make all distance traveled positive. Well, for part of this interval, velocity will be positive, in which case the absolute value bars don't do anything. And then for the other part of the interval, the velocity will be negative, and so it'll flip the sign of the velocity. And in fact, it's that first interval, so when t goes from 1 all the way up to 3, so you can think 1 is somewhere inside here, right? 1 is in between -2 and 3. So when you go from t equals 1 to t equals 3, let me label this as t. This is t equals 1 to t equals 3. The velocity is negative, and so the absolute value bars have to apply an extra negative to make the velocity positive, to flip the sign of velocity. So this is going to be negative v of t when you apply the absolute value bars on that interval. Then you've got the interval from 3 to 4, where from 3 to 4 velocity is positive and the absolute value bars don't do anything. You can just drop the absolute value bars on that interval. So if you wanted to write a note, you could say this negative here is coming from the fact that v of t is negative on that interval from 1 to 3, from t equals 1 to t equals 3. Okay, so there's our setup. We have the interval from 1 to 3 of, well, negative v of t. Let's see, where was v of t? It was way up here. There's v of t. T squared minus, yeah, actually, it's all the way up here. T squared minus t minus 6. So if you have negative v of t, that'll be negative t squared plus t plus 6. And then v of t itself, t squared minus t minus 6. Okay, we're going to find an antiderivative for each of these. We have negative t cubed over 3 plus t squared over 2 plus 6t from 1 to 3. Then we have plus t cubed over 3 minus t squared over 2 minus 6t from 4 to 3. We'll plug in our limits of integration. Gonna get pretty long here, I reckon. Now the key thing here is to remember to put a parenthesis when you plug in the lower limit of integration if you have more than one term, because that minus is going to distribute to each of those terms. So we have negative 1 cubed. over 3 plus 1 squared over 2 plus 6 times 1, whoops, plus, and then here we've got, in fact, I'm going to put parentheses around all these things. Each of these, every time we plug in one of these limits of integration, let's just put a parenthesis so we can separate things out here. So we have 4 cubed over 3 minus 4 squared over 2 minus 6 times 4. That's the 4 plugged in. Then we have minus, and then 3 cubed over 3 minus 3 squared over 2 minus 6 times 3. Close off those parentheses. I will spare you the details, but you can check this for yourself. This should come out to be 61 over 6. If it doesn't, give me a call. And that's 10 1/6 meters of distance traveled. Usually you like to write things in whole number and then fractional part. Great. Well, thanks so much for watching, and see you next time.